Please, and registering, I'm gonna have to go get a dongle. I'll be right back. You got a case? Yeah. Okay, case. Cards and rates and their statistics for biology.
Here we are. We're in our. Did you have a chance to go home for Christmas?
No, actually, my parents came to.
Really? Good. Good.
There's a couple places.
Where did you go?
Atlanta.
Oh, good. A little warmer?
Yeah, it's good. Or as close as you can get. So you know, that's good. And Orlando, probably.
Well, good.
Some warm weather for when you're in.
Yeah, this is
Just
just.
fun to make a lot of.
Yeah, this is. It's a blue.
It's just weird. Yes. All right. Welcome back. We were talking about prison data, and we were working on US data. And I realized that I asked you guys to go home and work a chi-square test without actually having taught you how to work a chi-square test. We're gonna be working through what chi-square tests are, how they're used, et cetera, here in a couple of weeks. But I want you to get in the habit of just taking these on and running with them, even if I haven't maybe given you complete information. But a couple of you came by between Wednesday and today to get help, and so if one of you could come up here and work out the chi-square test for us and explain to your peers what you're doing as you're doing it. And just so you know, this is a common practice for me to ask you to come to the board and do something and expose yourself to embarrassment, et cetera, but there's nothing actually to be embarrassed about. Probably before now, none of you have done a chi-square test, so that's that. There's nothing to be embarrassed about. Good. Once again, explain to people what you're doing as you're doing it.
Okay. I'll do my best. Okay. So basically, the first thing that we did, this is the observed. And we added these three numbers together to get this. This
before you do that, what do you have to generate from the population data?
So we have to do the frequency
Yep.
of population.
Yep.
And to get those numbers,
The frequency is just a decimal representation of the percentage, and so to the
Okay.
frequency, what would you do?
If we call that percentizing,
Yeah.
is that
Sure.
slang, but that's okay.
I've never used that term, but sure.
so we would do like this divided by this.
No, because you want to do it for population, remember?
Okay, so we did this divided by this.
You did that, divided by
Okay.
that, yep.
So we did this number divided by this number to get 0.783. Same thing here.
Did you say 0.783? Or 788?
Oh,
Okay.
okay, so those are things that we did yesterday. If you add those all together, you should get 1.
They should all add up to 100%.
Yes, yes. And then you would take this number times,
Times the total number of prisoners, so you could find out what the expected number of prisoners would be if prisoners were distributed the same way population was distributed.
yeah.
Good.
So you did that for each, and you would get, so we did this times observed.
Yeah, and this would be like observed total or something.
Okay, so now we have our expected.
And when you sum those three things up, what should they equal?
They should equal the observed total.
Exactly.
Okay, so now that we have our expected values and our observed values, we can do the chi-square test. I'll do it right here. This is observed minus expected squared over expected. And you do that for each of the observed values and expected values. So we'll start with the white. And then whenever you do the math, you get this number. And what this number means is that you would have fewer white people than you would expect to the total population.
In prison, you have fewer white people imprisoned relative to what you would expect based on their representation in the population as a whole.
Yes.
By like over 600, or, yeah, over 600,000 prisoners fewer than you would expect.
I'm doing the same equation for the black prisoners. this number means that there are more black people in prison relative to the population.
Sure. And actually, you don't even need that number down there. You can see that just from comparing observed to expected.
Yes.
You have 592,900 prisoners. You would expect 156,541 if prisoners were represented in the same proportion that they are, or that black people are in the general population. So.
Which is also shows you that there's more expected Hispanics.
There are way more Hispanic prisoners than you would expect if you used their representation of the population as a whole as your reference.
And then you would add these three numbers together. That means that chi-squared equals you want me to do anything beyond this number?
No.
Okay.
No, that's good. So you could also do this in a spreadsheet, and you could do it faster, because you could just copy formulas. So here I've done it for the US data, I've done it for the Missouri data. Basically, you have the prison population, the regular population. You can calculate the proportion of prisoners, the proportion of the population. You can calculate the expected number of prisoners. Why do our numbers differ? Oh, probably because I have more significant digits because it's saving things. We rounded a little bit. But it gives you basically what is essentially something very similar in terms of the total chi-square. This is going to give you slightly different answers because it's keeping all of these decimal digits. But what I want to call attention to is when you go online and you download a chi-square table. A chi-square table is just a table that essentially tells you for a given probability value and a given degrees of freedom, what is the chi-square value that you need to exceed in order to say that two distributions are different from one another. And in this case, we have 2 degrees of freedom because we have 3 categories, and the degrees of freedom is always 1 minus the number of categories that you're comparing. And if we're testing at an alpha of 0.05, this is a type 1 error rate. And the type 1 error rate, a type 1 error is when you basically say that for a chi-square, it's when you say that 2 distributions are different when in actuality they're not. So it's a type of error. It's concluding a conclusion that is ultimately incorrect. And we generally want to only make those kinds of mistakes rarely, and so we set the probability of doing that relatively low. And then what the table does is says, okay, so for that level of significance at 2 degrees of freedom, chi-square would be significant if it is greater than 5.991. Our chi-square statistic is over 1 million that we calculated from this data set.
Where's 5.991?
It's,
How do you work the table?
you go here to your alpha level,
Got it.
and then you come down to the number of degrees of freedom, and it's 5.99, and I just remember the one from a table that's in my office that has more digits in it. So, but you can also just go to a free calculator. There's this guy named Daniel Soper. I don't know him, although I love him, because he does stuff like this. He provides free of charge and through his own hard work and toil, a free statistical calculator. So you can go here to the chi-square distribution tab on his website, and you can get a p-value calculator for a chi-square test. And what this does is it asks you, what's your chi-square value? How many degrees of freedom do you have? And then it will calculate for you what the p-value is. So we can test whether his system works because we can plug in a chi-square value of 5.991 that we got from the table with 2 degrees of freedom. And when we calculate that, it should give us a p-value of 0.05, which is exactly what the table told us. So now let's put in our chi-square value and calculate what its p-value is. So the chi-square value is 1.763.595. We'll just round up. For 2 degrees of freedom, 1.763.595. When we ask it to calculate the p-value, we get an error message that basically says chi-square value must be a number between really close to 0 and 1,000. This is basically Daniel Soper's algorithm saying, what are you, kidding me? Who has a chi-square value that high? That's ridiculous, I'm not going to do it. Are these two distributions different from one another? The distribution across races and prisons compared to the expected distribution that you expect on the basis of population. Yeah, it's freaking ridiculous how different they actually are. You could do the same thing with the Missouri data, you could do the same thing with the world data, et cetera, et cetera. Here's the thing about statistics. These are the data. These data come from the US Bureau of Justice Statistics. These data come from the US Census Bureau. We're about to go through the census, so these data will soon be updated. These are two government organizations who are tasked with the process of keeping track of things. Keeping track of population in one case, keeping track of prisoners in another case. I think probably the Census Bureau is maybe doing a better job than the Bureau of Justice Statistics because of all the rounding that appears to be going on with the prisoner data. But even with rounding, these data are probably not far off the actual numbers. When we test them with a statistical test that is designed to see if there are two distributions that are similar or not with one another, we find that not only are they different, they're so different that you can't even calculate the p-value of it. That's like how radically, disturbingly different they are. So these are the data. This is the data as analyzed by an accepted way of analyzing it. And the answer that you get is that these two distributions are very disparate. As a statistician, you've done your job. We had a question. Do incarceration rates look skewed when you divide them up by race? And they appear to be skewed. Now what you do with that, after you reach that statistical conclusion, is in the realm of ethics and politics and finance and all of these other realms of human endeavor. What doesn't change is the numbers. What doesn't change is the analysis. What you do with those numbers in those analysis is a different realm of human endeavor. Ethics, morals, justice, social justice, et cetera, what you do with those numbers is a different issue than what those numbers are and what those numbers mean in terms of a statistical sense. I personally think we probably should look at our criminal justice system in the United States, because I was talking about this with a colleague yesterday, actually, in my department meeting, and she pointed out that these are incarceration rates. These are not crime rates. What's the difference?
Convictions. Is it convictions or how long they're in prison?
So incarceration has to do with, have you been accused of a crime? Once you're accused of a crime, are you convicted of a crime? Once you're convicted of a crime, does that criminal conviction result in incarceration or not? And how long is the sentence in that incarceration, et cetera, et cetera? Those things all go into incarceration rate. And she pointed out, and I knew this already without her pointing this out to me, that incarceration rate is different than levels of criminality. And so we have to unpack all of that. Those aren't statistical considerations, except in that when you look at incarceration data, you have to realize what incarceration data is rather than some other form of data. And it's always good to think about the form of your data before you enter into any analysis. But this was brought home to me a number of years ago because I was at home grading on a Sunday night, and I realized when I sat down to grade, it was winter, it was cold, it got dark early, it was about 6:30 or 7 on a Sunday night. I realized that I had forgotten my rubrics at home. I'm already in my pajamas, because it's Sunday night at 7 o'clock and I'm old. And so, it's like, I live 9 blocks from the campus, so I said, oh, I'll just hop in my car, I'll go up to campus, I'll grab my rubrics, I'll come home. And my partner is like, oh, well, if we're going up there, can we go to Sheridan's and get some custard on the way, or on the way back, actually. I'm like, sure, no problem. So I just went outside, hopped in the car, drove to school. I get about a block from the entrance to the college, and the police lights go off in my back window. I'm like, okay, what did I do? So I pull into the campus, and I pull into that first lot as you enter campus, and the police officer comes around to my side of the car and says, I need your driver's license and your insurance. And I said, what's the problem, officer? And he said, you have a burned out tail light. So I reach into my pocket of my pajama pants, because I'm in my pajama pants. Guess what I do not have? My wallet. So I have no driver's license. Okay, you don't have your driver's license because you're clearly in your pajama pants and you didn't put your wallet in your pajama pants. Can I see your insurance card, which was normally in my little console, but it was late in the semester. My insurance renews the 11th of November, and so this is the beginning of December. I didn't print off the new card and put it in my console yet, so I also don't have a current proof of insurance. So now there's a cop outside my window. I have no license. I have no insurance card, and my partner is substantially younger than I am. I have a white female, much younger than me, sitting in the passenger seat. I explained that I was headed up to college to get some rubrics that I had forgotten. I was already in my pajama pants, which is why I don't have my wallet. My insurance, as you can see on the expired insurance card, renews in November. I haven't gotten the new card in there yet. Blah, 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 blah. I'm just a big bag of sad excuses. He basically looks at me and says, get your light fixed, always carry your wallet, and get your new insurance card in your car. And then walks away. And I turned to my girlfriend at that moment, and I said, that is white privilege. Never in my life has white privilege been more stark to me. If I was a black man with a young white woman in my car, no license, no insurance, I doubt that I would have just had the police officer walk away from me. When we think about incarceration rates, we have to think about not only what is the level of criminality as it's distributed geographically, we have to think also about what leads to you ultimately going from an interaction with a police officer to ending up in jail. These are the data. The data indicate that we incarcerate colored people at a much higher rate than we incarcerate white people if our reference population is the population as a whole. What we then do with those data and the conclusions that come from those data is up to us as a society. What doesn't change is the data and the data analysis. Yeah, as your name Athos?
Yeah.
Pronounce it Athos? Yeah. Yeah, you had a question.
Yes, how do I calculate the expected population of prisoners? Because this is kind of like vague.
You take the frequency, so always you have an observed population that you're interested in.
Yeah.
And in this case, I'm interested in prisoners because I'm a pingo liberal. And you have a reference population. In this case, the reference population is the population as a whole. And so you have those numbers for your different categories, and you have the total. You then get the proportion of the individuals in, let's say that this is white prisoners, black prisoners, Hispanic prisoners. You take this number divided by the total. That gives you a frequency. And then you take this frequency and multiply it times the total prisoners. Then what you end up with is you end up with an observed column and an expected column that sum to the same number of individuals. So if my computer would stop not communicating with the screens here, so you'll see that the prison data are here, and they add up to 1,423,100, 1,423,100, and the expected prisoners also add up to 1,422,100, and it's because we took this population value, multiplied it times the total number of people to give how many, or sorry, this population frequency times the total number of prisoners to find what's the expected number of prisoners that we would expect if 78% of them were white. What is the expected number of prisoners if 11% of the prisoners were black? What's the expected number of prisoners if 10.7% of them were Hispanic?
Thank you.
Okay, so you always want to create an observed and an expected when you're doing this type of chi-square test, such that those two columns add up to the same amount. So, my purpose in doing this is to not harp about prison and incarceration, although I could go on. My purpose in this is to get across to you the point that statistics have relevance. You can look at a lot of issues that are out there in the world using statistical analyses and forms of statistical thinking to ask simple and then sometimes more complicated questions about the data that are floating around out there. And that's going to be hopefully a set of skills that you will take out of this class. When somebody presents you with a set of numbers, you can inquire things about those numbers. You can put those numbers to the test. In some cases, you can do simple back of the envelope calculations like this to inquire about those numbers. In other cases, you have to do more complicated things. But I'm always surprised when I'm listening to news reports and things like this. I find myself jotting down numbers because I'm curious as to where those numbers came from, what they mean, et cetera, et cetera. And then I go and I think about those numbers and I'm like, man, that just ends up being total bullshit that somebody just told me. So I want you to start getting into a statistically thinking frame of mind by confronting you with some real world data that ultimately have real world consequences for real world people. Sadly. Questions about any of this? Don't worry about the mechanics of chi-squared at this point. We're going to cover that in a couple of weeks, and then at that point, I'll be expecting you to learn how to do this. Today was just playing around with numbers for a little while. Tom, the other day, kept mentioning that we should be calculating per capita rates on all of this stuff. So I went back in the interim and I altered the R script to do per capita rates. So I just want to show you that. So just to give you an idea, I haven't gone through the syllabus yet. You've maybe noticed that. We haven't covered the syllabus yet. We're going to get to that. When we go through the syllabus, one of the things that you're going to see in the list of assignments is for everything that I asked you to do, the first thing that we will do is we will always work that out by hand. So when we do chi-square tests, the first thing we're going to do is we're going to do chi-square tests by hand on the board, pencil and paper, calculator. The reason that I do this is I want you to know how the statistical test operates. I want you to know the mechanics of it. We'll work a set of problems by hand so that you learn the mechanics, and then I'll give you a problem set that asks you to practice that, and then you'll turn that in, And then you'll get a bigger, more complicated data set that you will analyze on the computer, and you will write a report. The report will basically consist of a statistical methods section. The statistical methods section will include a description of the data. Essentially, what are the kind of data that you're about to analyze, what the analysis is that you are planning, and how you are going to make decisions about those data. Then there will be a results section where you will then communicate the results of your analysis, and then there will be a brief discussion section where you explain, in terms of the original data, in terms of the question that was being posed, et cetera, what those data mean. So the results and what they mean are related, but they're different in the way we talk about them. The results are just blah, 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 this is the result. The discussion is, this is what that result means and how it should be interpreted. And so for each technique that we use, we're going to have a problem set that you will work out by hand, and then you will have a project that you will work out with a more complicated data set that you could work out by hand, but it would be much faster and more efficient to work it out via computer. And for those data sets, you'll write a short report explaining what the data were, what you did to the data, what you found, and what it means. And that's going to be the sequence. Introduce you to a set of techniques, make you work on those techniques by hand, make you work on those techniques on the computer, write a report, move on to the next technique. Before we get to that point, we're going to talk a lot about theory here at the beginning, because if you understand sampling theory and you understand the nature of distributions and how they relate to statistics, it becomes very easy to deal with any new statistical technique that comes up. And so one of the reasons that in the latter part of the class we can cover so many different kinds of techniques is because each of those techniques is based on basic sampling theory and distribution theory. And if we have a good fundamental understanding of those things, it makes everything else we do in this class easier. So there's one exam in the class. It comes at about week 3, at the end of week 3, beginning of week 4, and it is on theory. And then there are no more tests the rest of the semester. It's all problem sets and reports from there on out. This is definitely a class where you get your grade by proving that you have the ability to do the task, which is kind of nice.
Amen.
Because ultimately, when somebody comes to you and says, I have a statistical question, the question that they have for you, you either have the ability to answer the question and do the analysis, or you don't. And so this is a class that is definitely all about doing. So the more practice you have with things, the better you're going to be at those things. And so we're going to spend a lot of time practicing. Practicing my hand, practicing my computer. So I was about to talk about R, which is how I got distracted by the syllabus. So when we go through R the first time, when I'm actually teaching you a technique for the purpose of you learning the technique, I will walk you through the R code line by line, because I want you to understand what the R script is doing, what the syntax is about, what the code actually means, because you have to learn the syntax in order to get R to give you what it is that you want it to give you. I didn't do that with this one because that's not really the purpose of this exercise. But one of the things that I have gotten in the habit of doing over time is I've gotten in the habit of annotating my R scripts pretty heavily. So all of the green that you see in this with a hashtag in front of it, with a pound sign in front of it, these are all comments. And I would advise you in any of your computer programming, whether you're doing Python or you're doing C or whatever, that as you write programs or write scripts, that you heavily annotate those things. Because what happens is, you write a program to do a particular task, you come back to that program 6 months later and you look at it and you're like, okay, what did I do there? And so leaving yourself explanations of what you're doing and why you're doing it that particular way in the commenting ability of your coding is always useful, because if you go away from that code for a little while and come back to it, you can figure out what the heck you did and why you did it that way. So you're going to see a lot of comments here. The other thing is, you'll notice that in this script, a lot of the code looks very similar to one another. So once I have a data set built, so this is the world data set, I had to do a number of things to get this data set to work. I had to get the data in. This is an assignment. This is what we call an assignment operator. All it does is it looks kind of like an arrow, and I think of it like an arrow. And all it does is it basically says, take this thing that is on this side and call it that. And so what I'm doing here is I'm asking R to read in a CSV file, comma separated values file, read it in, and call it world inc, so that I don't have to call it up every time. Anytime I type in world inc, it will just assume that I'm referring to that data set that I've already read in. Then this basically says, give me the first 6 lines of world inc so that I can see that it's read it in correctly. So I can go here, read in world inc, and then I can get a list of the first 6 lines of world inc down here. And it tells me what the prisoner population is, the general population is, and it tells me the countries. It gives me an indication that R saw my data and it read it appropriately, and it's giving me the data correctly.
Where's the 6? Where's it 6?
Where's what 6?
Well, you said somewhere you told it to give you 6 lines of data.
Oh, yeah.
Where's the 6?
1, 2, 3, 4, 5, 6.
But if I needed your code.
Oh, head. Head is just,
Oh.
head, when you say head, it just gives you 6 lines.
Okay.
That's what it does. I didn't tell it to do it, it told itself to do it. So when I first downloaded the population data, I downloaded it from a website that had population data, but the data were entered as text instead of numbers. It had commas in there, and so it appeared as text rather than numbers. And so this class world inc population thing just tells me what kind of data do I have, and it's numeric now because I've altered it. But when I first did it, it was text. It was actually it said factor, which is R's way of saying text. And so I had to go through and finagle it to get it to convert that text data into numeric data. But now it's numeric data, so everything's fine. When I made the histograms the first time, the default in R is that it does things alphabetically. And so it put the United States way on the end of the data set. And what I wanted to do was I wanted to create a histogram that was ranked from most incarcerated prisoners to least incarcerated prisoners. So this couple of lines here is basically just me forcing R to put it in the order that I want it to be put in. And I can test this by looking at levels. I can see what the levels are, and if it has worked, it will have the United States, Brazil, India, Indonesia, United States, China, Brazil, Russian Federation. They are in the order that I want them to be. And so now I can just make a plot of them. And we saw what this plot looks like. We did this before. It's going to take it forever to render. But there it is. It's squunched because it's just a ton of stuff to put in there. But so I had all of this in place, but then Tom kept asking about per capita rates. So all I did was just get R to calculate per capita rates for me. So originally the data set had a column for country, a column for prisoners, and a column for population. All I'm doing is I'm saying, in the world inc data frame, make a new variable per capita, calculate, so I'm basically saying, take this and call it that. Take this and call it that. The number of prisoners divided by the population times 100,000, what that will do is it will give us the number of prisoners per 100,000 people. It's a way of expressing the per capita rate. And when I do that, I execute that line of code, and what it has done, it has now added a new layer of data, a new column of data, that is the per capita rate of incarceration. And so I did this for all of them, and so we can see down here when we look at the top 20, I have per capita rates from the top 20, and we can also make a graph of the per capita rates of the top 20, and once again, it tells you exactly what we already knew, which is that we incarcerated a ton in the United States for whatever reason. So, but what my point in showing you all this was, once I have the data in, and I have it arranged in the order I want it in, and I check that, and I make a plot of it, I don't ever have to recreate all that code again. I can copy that code, paste it down below, and then when I get to, I can do this, once I do that, I can copy this ggplot code. This is the code that gave us that histogram. I can copy that, paste it down here, and just change what's being graphed from the prisoner population to the general population. Nothing else in those lines of code changes. And it produces a graph that looks exactly like the other one, except that it now has different white data in it than it did before. And then once I have that done, I can copy that whole thing, and instead of dealing with world population as a whole, I can deal with the top 20 countries. And then once I have that, I can copy all that down below and just change the data that are being used from Worlding to US Inc. to do the US data. So once you have some base code that works and does the thing that you want to do, you don't have to recreate that code over and over again. Just copy and paste and have it do it again on either a different data set or a different variable or whatever. So scripting in this way might seem daunting at the beginning, but once you figure out how to do one thing, your life gets much easier. And you've probably discovered this with your coding classes that you've had in your data science program. So what I did was I just calculated per capita rates. So now on the Moodle site, which we haven't really gone and talked about, but we're about to, I now have in today's material the data sets that this is based on, and the R script that produced all of this is in there, so you can go in there and start playing around with R if you want. Now, all of the computers in here have R loaded on them. They're actually loaded onto a hard drive. They're not server-based. Somebody last semester in IT, I sent them an email and said I need R and RStudio on every computer in that room, and they came in here and they did it, so I didn't have to, thank God. But they're just base R. There's no packages loaded or anything else. So as we do more and more things in here, you'll see at the beginning of this that I have loaded a set of packages. The mass package, the ggplot package, tidyverse, and forecats. These are all packages that are required for me to do the things that I'm doing in this. Your computers, except for this one, because I was playing around on this one, yours don't have any packages loaded beyond base R. So my advice to you is sit where you're sitting day to day. Don't move around the room, because you're going to populate the version of R on that machine with the stuff that you're using. So if you bop to another computer in the room, it's going to have possibly a different set of packages. In many cases, you'll have many of the same packages because you use the same packages over and over and over again. But your R version will start to look tailor-made to you, and you'll get used to it on your machine. And if you move to another machine, it's going to be different. You're going to expect things to be there that aren't, and then you're going to have to spend some time loading packages and things like that. If you type in, if you call up a package using the library command, and it doesn't just give you that library without any errors, it hasn't installed the package. So installing packages is really easy. you just go over here to the Packages tab. It will give you a list of all the packages that are in your resident R package. I use R a lot. So I have a lot of packages that are already installed. And it will also tell you which ones are activated. So for example, I am using ggplow right now. I am also using mass right now, so those have checks in front of them. So if you need to install a package though, just click on install, type in the name of the package it is that you need. Let's say that we need PastX. As you're typing, if there is a package that matches the string of characters that you're putting in there, it will pull it up, and then you just click install, and you'll get a bunch of error messages that aren't really errors, they're just telling you things about the installation process. And then after that, that package will be installed, and then you can activate it using the library command. So here at the beginning, when we're adding packages to these computers as we go, there are going to be times in class where we're actually all just sitting around twiddling our thumbs waiting for packages to install. But we're going to do a certain amount of live coding. In your data science classes, do you do a lot of live coding in class? Some? Okay. We're actually going to do a surprising amount of it. When we get to that point, I will always have in my bag of tricks here, I will always have a stack of Post-it notes. And the purpose of these Post-it notes, how do you, well, I don't know how you do live coding in your other classes, but everybody will get a Post-it note, and these Post-it notes will hang out on the sides of your computer. And when we're live coding, you're gonna see me running around a lot. I'm gonna be up here, I'm gonna give you a task, and then I'm gonna be running around the room making sure that you're accomplishing the task. The Post-it notes are so that when you're done with the task, you put your green Post-it note up, and then I know that you've successfully finished that task. If you've tried that task and something went wrong, and something always goes wrong, the orange one basically says, I'm trying to complete the task and it's not working, can you please come and help me? So that if I'm at the back of the room helping somebody else, I can just glance up, I can look around, anytime I see a yellow tab, that's when, orange tab, that's when I need to go to the next person. The other thing is, I don't have to keep querying you for a raise of hands, who's finished with the task. When I look around the room and I see nothing but green Post-it notes, I know everybody's finished, and I know we can move on to the next stage. So, always have a stack of these in my bag. You don't have to remember them each day. As a matter of fact, my advice would be to just stick them to the side of the computer and leave them there. If we come back the next day and they're not there, and we're going to be doing live coding, I'll just throw you some Post-it notes and we'll replace them. It's a good, efficient way of doing live coding. Live coding can feel chaotic. Just embrace the chaos. Questions? Yeah.
If you wanted to use your personal laptop,
You can, yeah, certainly. As a matter of fact, I would advise using your personal laptop because then you can take it home with you and do it at home. So you need to have, so this is in the syllabus. So, well, let's go to Moodle. Pull up on either your personal laptop or your school computer there. Pull up Moodle. Was everybody able to get on to Moodle? Okay, cool. So I've got the semester broken up by week, and what I've gotten in the habit of doing over the years is for each day, I'll put a folder in there, and in that folder should be everything you'll need for the day, whatever day we happen to be doing. And so when you click on the folder for today, I'm gonna get into student mode here so that I can show you what it looks like when you're doing it. So like today, materials for Friday, 24th of January, I have a bunch of things in here. I have the coin flip R script, which we're going to talk about later on today. I have some readings for you. I have an activity that we're going to do in class today, so you'll need to pull that up here in a few minutes. I have the data sets that are used, the Missouri data set, the US data set, the world data set, the top 20 world data set, that are all used in the prisons R script that I have up there. So kind of everything that we've done today is in this folder. Yeah.
are we reading the syllabus today?
Yeah, we're going to go through the syllabus here in a minute.
So
So if it's in the folder, what's a pre-read and what's a do in class?
I
How
want
do
you,
sort that?
if it's in here for today, I want you to have it read by today. So read chapter 1 in Quinn and Keogh and read chapters 1 and 3 in Matulski. So 1 talks about probability, 2 talks about distributions. We're probably not gonna get much to distributions today, we'll get to that on Monday. But if you haven't read it for today, then definitely read it for Monday because it's gonna be super important on Monday. So yeah, so if I give you a reading assignment for a day, I want you to have it read for that day. Yeah, it's a preparation thing. Yeah. So let's go to the syllabus. I don't know why I guess I don't know. I now have like 50 copies of my own syllabus on my computer.
Yeah, yeah. That happens to me too.
Okay, so here's the syllabus. Office hours are times when you should just assume that I'm sitting in my office waiting for you to come by and see me. If you need to see me outside of office hours, give me an email. Grace emailed me, said, hey, I need to talk to you about chi-square test, which is how she knew how to go through this today. And make an appointment with me. I'll come up if I'm not on campus, or I'll make sure that I'm in my office. If I know a time that you're coming by, I'll be sure for you. My office is next to the horse skeleton over in White Science Center. So this is learning outcomes, all this jazz. There are websites for the R stuff that you need to have. So you need R and RStudio. R is base R. You need that in order to run RStudio. RStudio is just a graphical user interface that makes R a little more user-friendly. I use RStudio because it has some advantages over base R. Talks about the course structure. I suspect that you're going to have a really difficult time in this class if you don't come to class, because we're going to be doing a certain amount of live coding, and the textbook is actually really good and really self-explanatory, but it's also advantageous to just have somebody who's a human telling you about these things as well. But certainly when we start doing a lot of coding, a lot of scripting, you'll want to be here in class for that, so you'll be here. A bunch of this is boilerplate stuff that you'll find in every syllabus because it's just college policy. Turn off your cell phones. You have to have your computers here, so by all means, bring your computers. The thing about iPads is R doesn't run on iPads, so if you're going to run software, if you're going to run R, you have to have a computer, so you either bring your own laptops if you prefer that. I would advise you to bring your own laptops, and if you don't have a laptop, then the reason that this is taught in this classroom is because everybody has a computer. The drop date is relatively late here, and then these are the assignments. So, as I explained before, for everything that we do, there's going to be a coin flip assignment that I'm going to give you here in a few minutes, but then there's always a problem set, and then doing it. Problem set, doing it. Problem set, doing it. Problem set, doing it. That's the structure of the course. I introduce you to a technique. We're going to work it by hand in class. You're going to work it by hand as homework. Once we feel like we've gotten you the mechanics of the technique under your fingers, you're going to get a big data set, you're going to work that data set, you're going to write a report on it. There is, whoa, son of a bitch. There's no exam up here. There will be an exam. I need to add that to this. So I'll post a revised syllabus. So it's a really simple syllabus. Basically, you're here to learn about statistics. I'm here to teach you statistics. How do you learn statistics? You learn statistics by working statistics. Also on here is a daily schedule. I now have more copies of the daily schedule that I need as well. This is a schedule that has actually worked out for a number of years now, so I think we'll probably be able to stay on schedule for the most part. meetings to this. So today we're going to be talking about sampling theory, and we're going to be talking about the syllabus. So this is what we're doing now. Yeah.
Can you show us how to download the R program that you were talking about?
Yeah. So.
Because I checked here to see downloaded and all the universities on here.
Oh yeah, no. So these are just universities where they have R on there. So you want to go to someplace nearby. So just go to what version?
I know, but isn't it good? I have no idea what to do.
Okay, go ahead. Yeah, so you want the most recent version, so you want 3.6.2. So these are just version numbers. So when you download that, it's going to download it as a zip file, and then you'll have to explode it, and it should give you an execute file. And if you have problems, come by and see me in my office hours. So there will be an exam on the 19th of February, and it will cover everything that we're covering through this section. And you'll see that this is all about sampling theory, distributions, power and probability, distributional tests, because when we talk about distributions, we want to be able to test those distributions. This is why we're going to be doing chi-square and Kolmogorov-Smirnov and Shapiro-Wilks test, things like this. And then we'll have some simple statistics that are easily worked out by hand that will be on the test. They get across to you some of the basic ideas of hypothesis testing. And then we'll have an exam. And then after that, it's all just, here's a technique, here's how you do it, here's a non-parametric version of the technique, and then you'll get an assignment. Here's a new technique, just instead of one-way ANOVA, now there are two categorical variables. Two-way ANOVA, here's the technique, here's how it works. Here is the non-parametric version of the two-way ANOVA, and then you'll get a project to work on. Then we're going to talk about regression. We'll work out regression by hand. We'll work it out by hand, we'll do a project on it, and then we'll move on to multiple regression. And then we'll do that by hand, which is a total pain in the ass. And you'll do a project on it, et cetera, et cetera. It's just same process, new technique. And we are going to waltz through a lot of new stuff for you. In almost all cases, the data that you're going to be working with are actual data. Can I borrow your book? Sure. So this is a book that I use, and I use it for a couple of reasons. One, the language that it's written in is written for biologists, so it's written by biologists for biologists, and biologists are not statisticians. So it's language that is approachable, that you can wrap your head around. The other reason is that every example in the book, this book has a website, and the data files for those examples are on the website. So the example is worked in the book, the data are on a website, we can download the data, we can run it by hand, we can run it through R, and we can make sure that we're running it correctly because the solution is in the book, and the data are on the website, it attaches to the book. The other thing is these guys are practicing biological statisticians, and so they don't get so caught up in a lot of the theoretical controversies that can really bog you down sometimes if you think about them too hard. They're capable of doing it. They wrote, Jerry Quinn wrote a paper in 1989 that really got bogged down in controversy about what you do with data after you've concluded that something's different in analysis of variance. It's a really long, complicated, dry paper, really heavy on theory. So they have good statistical chops, but the purpose of this book isn't to explore those kinds of things. The purpose of this book is to teach you how to do statistics. And so it's a pretty good book. It's one of my favorite books, and that's why, those are all the reasons that we're using that book. At the end of the semester, I'm going to have a person come in the last week and a half, who is a person who does bioinformatics, works with really large data sets, and that's not something that we're going to do in here. All of our data sets, even the big ones, are going to be relatively small. but she deals with really big data sets, deals with genomic data. But once again, the basic distributional lessons that we learn here in the next couple of weeks are going to be able to be applied to those things. And when we talk about distributions here in next week, I'm going to show you an example of how I myself struggled with thinking about genomic data until I read a paper that approached it in a way that basically took a distributional and sampling theory approach to explaining what genomic data analyses are. And I saw this one figure in this one paper, and as soon as I saw that figure, I'm like, that's what's going on. Because it spoke to my own background in theoretical statistics, where distribution and sampling theory are the things that drive everything in statistics. And so I'll show you that as well. So there's nothing scheduled here at the end, because for one thing, we're probably going to get off schedule a little bit over the course of time, but then I also have that time arranged at the end for somebody to come in and introduce you to techniques that you will not work out by hand because you can't, because they're too big, and that you won't write a project paper on, because once again, it's the end of the semester and the analyses are complicated enough that it will give you some insight into what you can do maybe down the line with statistics if you want to go that direction. Yeah.
On the schedule,
Yeah.
10th of April, is that a real, no kidding, 4-day weekend?
Yeah, Good Friday and Easter Monday.
Good.
I don't know why we do that, but we do. We're good with that. And also, just so you know, I'm gonna be at a conference, oh, it's not gonna affect anything. I'm gonna be at a conference on the 23rd and 24th, so I won't be here. But we don't have class on Thursday. Oh, but Thursday that day is a Friday schedule, so we won't have class that day. We should have class that day, we won't have class that day, because Paul's going to be at the Allied Genetics Conference. So, no class then. Questions? All right, we have used up far more time than I thought we were going to use up. So, rather than burn up time in class, I'm just gonna assign this as homework. Go to the Moodle site, click on some basic concepts in probability and sampling. Do you guys have quarters? Do you guys carry change? Yeah, I know, it's hard. Like, I needed quarters for today, and I had to go to the Quick Trip this morning and say, can I buy $3 worth of quarters from you? And it's like, sure. So I have a quarter. Take this quarter with you over the weekend. Do not spend it on gumdrops. You need to get together with a partner in class, because this task is a partner task. Coin flipping. I'm going to each of you a quarter, because I know that people don't carry change. Bring this back on Monday. It's like $3 that I'm out if you don't bring back my quarter. I'm a college professor, I don't make that much money. Basically, team up with somebody else in the class. Over the weekend, do the task. This is about coin flipping. When you flip a coin, what's the probability of getting a head? What's the probability of getting a tail? Okay, so your task is you're going to be flipping a coin a lot. So what I want you to do is, once you get together with a partner in class and have completed this first section, I want you to put those data in a Excel file and send it to me. I will put together all the class's data, and then I will ship a data file that has everybody's coin flipping results all together in one big file that you can then play with. And we will play with coin flipping a little while. They ask you to do some simple calculations on frequencies. There's a little web tutorial thing that has the ability to put data into it so that you can do some simulations online. And then at the end, there's a Radiolab episode that I want you to listen to, because it talks about probability in kind of a fun and interesting sort of way, and it tells you when you can stop listening Because there comes a point in the program where they start verging away from probability and start talking about other things. And then there is an R script on the Moodle site that basically takes all this stupid coin flipping that you did with your partner, and it makes R do the coin flipping. So rather than doing 100 coin flips, you can do 1,000 coin flips. You can do 10,000 coin flips. At the end of the R script, this is the coin flips R script. At the very end of it, and once again, this is a heavily annotated R script. This is an R script written by a former student in this class who we did the coin flip exercise, and she sat down and she said, oh, well, why can't we just do that in R instead of sitting in class flipping coins? And so she wrote this, and at the very end of it, it says, the histogram probably does not quite look like a binomial distribution, so rewrite the code above and do it for 1,000 trials rather than 100 trials. So go back up to this last snippet of code up here that she has written, copy that code, and then alter it such that it gives you 1,000 trials of coin flipping rather than 100 trials of coin flipping. Okay? And so that's your homework for the weekend, and you're out of time. Questions? So find a partner for coin flipping before you leave today. And enjoy your weekend of coin flipping.
Oh, no, we got this, we got this.
Did you check and see if you?
I sent out an email to confirm. So it works.
No, no problem.
I go by my email today.
9 a.m. for cancel by 7:45.
Okay.
So it's kind of fun.
Is anybody in the Python class that's right after this?
It got canceled.
It got canceled. So those of you who have a canceled class can stay here and coin flip.
Yes.
Oh, when you coin flip, just so you know, don't catch it. You have to let it hit and bounce. So if you ever watch a football game, you notice that when they flip it, they let it fall to the ground and bounce around. When I was in elementary school, I trained myself to flip coins so that I knew what the outcome was going to be. I practiced at home, and I went to the playground and I ripped off other kids' lunch money by betting them whether or not I could predict the flip of the coin. Because even as an elementary school, everybody knows the flip of the coin is random. If you practice and you toss it and catch it, you can actually determine the outcome. So don't catch it. So many gumdrops and so many sweet tarts bought off of lunch money from the playground because I trained myself to flip the coin. Probably should admit that.
Hey, Paul.
Yeah.
So, any Python class here?
The coin flipping part. Once you're done with coin flipping, you can go off and do things on your own.
So just,
I'm very free, so whenever
Yeah.
you're
so if I
available.
wanted to do 100 by myself.
You can do 100 by yourself. It's quicker if you have somebody flipping and somebody recording.
Sure.
And-
Well, I'm gonna be off campus most of the weekend. So
Yeah, just do it and submit it. You don't have to. So the first time that I taught this, I was in Hawaii doing research for the first week and a half of classes. So this was something that I could send to students that they could do in class with me.
So,
Actually, I should have all done this stuff and interact with them. They were in class doing this exercise pretty much on their own. And so we would normally do it in class if the time management had gone a little better. But it's not done.
Okay, I'll be by the coffee shop.
it's just quicker in a classroom setting if you have somebody reporting on somebody flipping.
Then it's